All right, good morning, everybody. How's everyone today? All right, good morning, everybody. Had my microphone muted, rookie. How's everyone today? Good, good. All right, let's start with any questions. All right, well, let's go ahead and talk about adders then. So lab 3, good job for people who followed the instructions. You generally scored high on the lab. People who did not score high on the lab, generally it wasn't a digital logic issue. It was more an issue of just missing some of the steps or minimizing before you should have, and so on. So following the instructions basically. And lab 4 will be very much the same. So I want to talk more about adders. We started talking about adders on Wednesday. I want to finish up discussing that and then run through Lab 4 briefly one more time and tell you how that relates particularly to the specific steps you need to do to get full credit on Lab 4. And then we're going to go ahead and we're going to start basically the second half of the course, which we'll talk about when we get there. But everything we've done so far has been kind of preamble. It's been building up the tools we need to really launch into the sort of heart of Engineering 250. So we'll be getting to that in a little bit today. But let's start with this idea of adders. And we were thinking about 2-bit adders. And so a 2-bit adder means it's adding 2-bit numbers. And adders generally add two things, so A and B are each 2 bits. And so if I wanted to draw a system diagram, it might look something like this. A1, A0, B1, B0, sum 2, sum 1, sum 0. And I might say something like S2, S10 equals sum of A1, A0 and B1, B0. Now, the numbering of these inputs and outputs is critical. Okay, this came up in one of the homework questions also, where we were trying to find f of A, B, A1, A0. The order is really important. So when I write B1, B0, the pretty much universal understanding is that this is the most significant bit, this is the least significant bit. This is not 100%, but it will be 100% in every course that you take with me, including this course. So least significant bit, that's the ones place, right? If this is a 0, it's 0. If it's a 1, it's a 1. Most significant in this place would be the 4's place. So this is 1, 2, 4. Here it's just 1, 2, 1, 2. So a number like 1, 0 represents 2 as opposed to 1. 0, 1 represents 1. Over here, a number like 1, 0, 0 represents 4. 0, 0, 1 represents 1. But you could find places where that is switched, but not in this course. So most significant, least significant, and we use these rather than left and right. Most significant is the one that multiplies by the greatest, power of 2. So it's really important when you sketch your system diagram for your lab or for anything else that you know what these 3 outputs are. Because just saying S2, S1, S0 does not in itself tell you that S2 is the most significant bit, so make sure you indicate that somewhere. And of course indicate that this is the sum of this number plus this number. Because, you know, somebody else could say, hey, this is going to add these two numbers, A0, B0, and A1, B1. Well, that's a completely different circuit. It's still a 2-bit adder. But, you know, maybe my first number is represented by A0, B0. My second number is A1, B1. Totally different circuitry. So make sure it's really clear to somebody looking at your system diagram what the function is. Right? And this is the design process we keep doing. We keep starting from, you know, problem, going to a system diagram, going to a truth table, going to equations, going to a schematic, going to, you know, a physical circuit, or Tinkercad in our case. And you need harmony here. If your physical circuit does not match your schematic, it's not a valid report. If your schematic is different from what your equations say, it's not a valid report. Your goal is always somebody else can take your report, reproduce your results. So if you do all of this stuff dutifully, and then at this point you say, I don't want to write those equations, I'm going to do a different schematic. And then you try to build it and it doesn't work, and you're like, oh yeah, I needed some extra wires, and you put those in your circuit. Well, great, you got a circuit that works in the end. That's worth a lot. But in terms of a lab report, somebody else trying to get there from the beginning, they can't follow your steps because those steps are missing. So make sure all of these have harmony, and it begins with a good system diagram. All right, so what's the behavior? Let's see. If you have time, do you mind going over how a switch could have a floating input? So sure. So this came up in a few of the labs. Here's an AND gate. This is connected to ground. This is connected to nothing. So what is the output here? Well, let's call this A and B, and let's call this X, and let's look at the truth table. And we know that if B is 0 and A is a 0, X will be a 0. If B is 0 and A is a 1, X will still be a 0. So in this case, we know that whatever A is, the output is going to be 0. But now let's take B and connect that to 5 volts. Well, now if A is a 0, X will be a 0. If A is a 1, X will be a 1. So what's the value of A here? Is it 0 volts or 5 volts? No way of knowing. It's not connected to ground, it's not connected to 5 volts. And it may seem like not connected to anything is the same as ground. If you've ever played in a rock band with badly grounded amplifiers and touched your bass strings to a microphone, you understand that not connected to anything is not the same thing as 0 volts. Right? This could be 0 volts, it could be 5 volts, it could be 10 volts, it could be negative 6 volts. So in general, unconnected inputs, we call them floating. And you can't predict what their voltage is. Now some types of logic, 74HC chips, will let you get away with different things. For example, a 74HC chip, you can get away with putting in 5 volts without going through a resistor. That's that particular type of logic chip. An old school TTL chip, if you did not connect an input, it was treated as a logic 1. The circuitry inside pulled it up to 5 volts. But from a logic design perspective, this is listed as an unknown, and so the output is an unknown. So if you will build your switches like this, your switch only works half the time. If I close my switch, now I have this input connected to ground, that's a logic 0. I'm all set. But if the switch is open, this is floating, no way to know what that input is. So how do we avoid having a floating input? Pull it up through a 1K resistor to 5 volts, so that if the switch is open, this is a logic 1. It's connected to 5 volts. But if the switch closes, Your current goes through here to ground, that's a 0. So now open is a 1, closed is a 0. So that's the only proper way using one of these switches that's either open or closed to be able to control the logic input of say, a gate. And that was that series of experiments in the prior lab where you had 2 switches and inverters and 3 configurations and all of that stuff. That's what that was exploring.
Yeah, I had a question.
Okay.
So, we're mainly using Tinkercad. Well, like, we're specifically using Tinkercad.
Mm-hmm.
I was just wondering, since, when I was doing the lab, when I implemented this schematic into Tinkercad, it wasn't working. So I fixed it by doing the floating input version. And I was just wondering how we should go about trusting Tinkercad, because you emailed me saying that yeah, it's not correct and stuff like that. But how should we be able to know what's right and not?
Tinkercad is not the goal, right? Your real goal is to produce a quality schematic that uses the techniques we've been going over in class, including, how to wire switches, LEDs, things like that. And then Tinkercad is kind of a demonstration that schematic works. In a physical laboratory, for example, when you have an output, you can run it through an LED directly to ground, and it will usually work. Now, if I hook a battery up here, the LED will blow, but if I just use the output of a gate and I don't have the resistor, this will still light up, right? But if your schematic did not include a resistor in here, you would still lose points. Because we've said when you wire an LED, you have to have a resistor in series to limit the current. So same thing with switches, right? If you have an input to a circuit, pull it up to 5 volts through a 1K, and then use the switch to conditionally ground it by closing the switch. It's a good question, though. I mean, and this is part of what this course is about, right? You can put components together and get a circuit that looks like it acts correctly, but maybe it's drawing more power than it should, or maybe it's stressing the components, and they're going to fail after 30 days, right? Because they're being worked outside of their intended operating range. And so having a circuit that you can run on a proto board or in Tinkercad, pretty good indication that things are mostly right, but it's not a substitute for making sure that you're following, our descriptions of how to wire switches and LEDs and things like that. Does that make sense? It's something that comes up for computer science students, at least in programming classes. We'll write a program which says, write something that plays tic-tac-toe. So a person clicks and it draws an X, and then the machine makes a move, and so on and so forth. And you can write the code for that and play the game and have it look great, and then hand it to your teacher, and they'll play the game, and they'll find 5 different ways in which the program fails. Right? So how do you test something enough in enough different situations to have confidence that it works? Well, it's a hard thing to do, right? It's a whole field of work in industry. But your better option is, if you understand the code that you're writing, and looking at the code, you're convinced that the program works, right? Then you almost just test it as an afterthought, right? Let's make sure that this is actually working correctly, instead of trying different things until the program looks like it runs well. So it's a good question, and it's a challenge that will come up again and again. For these kinds of circuits, switches and LEDs are always gotchas. And my only advice is switches, pull the input up to 5 volts through a resistor, use a switch to let the person close it. LEDs, always take the LED, run it through a 1K resistor in series, and if you want one to turn it on, put the cathode to ground. feed the anode. If you want to do one of the fancy LEDs from that earlier lab, you can flip this around and so on. All right, so 2-bit adders. We've got our system diagram here. System diagram leads to a truth table. So let's write a truth table for a 2-bit adder. And this is all topical for Lab 4. This is all stuff that is going to be critical for getting credit for your work on Lab 4. And I don't want to do the entire truth table for you because that's part of the lab, is coming up with the truth table. But we'll do a few rows in the beginning and a few rows at the end. So it's a 4-bit circuit. It has 4 inputs and it generates 3 outputs. So your truth table has got to have 4 input columns, 3 output columns. Right? If you don't have 4 and 3, all bets are off. But how do we figure out what these output columns are? Well, I'm going to add some more information in here. I'm going to put in a column that I'm going to label first number, which I'm going to call B. And I'm going to have second number, which I'm going to call A. Alright, well, B is just, what these 2 bits represent. Remember, B1 is the most significant bit. Well, 0, 0, that's just the number 0. 1, 0, that's the number 1. 1, 1, that's the number 3. And then second number A, well, 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. Here's a 0, here's a 1, 0 is 2, 1, 1 is 3. So these 16 rows represent all the different ways in which we might specify 2 2-bit numbers that we want to add. So I'm going to label this column sum of A and B. So what do we get when we add these 2 numbers together? Well, 0 plus 0 is 0, 1, 2, 3. 1 plus 0 is 1, 3 plus 2 is 5, 3 plus 3 is 6. So that's the information we want out of our adder for these combinations of 4 input bits. We want to know what this sum is. Since our output is a 3-bit binary number, S2 is the most significant bit, I'm just going to write each of these sums as a 3-bit number. 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. Here's 0, 0, 1, here's 1, 0, 1, here's 1, 1, 0. And you get to do all of these ones in between. So, good time to ask if there's any questions about this truth table, what it means, where it came from, how we would fill in the rest of it, what it's for, anything about this, because this is going to drive the equations and the schematic and so on and so forth. Alright, so from here we go to equations. And what are your equations going to look like? S0 equals something, S1 equals something, S2 equals something. And where do you get those? Typically sum of products. And if you write those equations, they're going to be pretty long and complex. Is there a reason B1 has 0, 0, 0, 0, 1? What are you referring to? And B0 has 0, 0, 0, 0, 0. The numbers here? So I ordered these in the usual way we order a truth table with 4 inputs. And these 2 bits over here correspond to B. These 2 bits correspond to A. And thank you. We could do those in a different order if we wanted. And eventually this information would appear in some other row. But B is just, you know, the number represented by these 2 bits. A is the number represented by these bits. So I'm not sure I see a 00001 in here. So that's B is 0, that's A is also 0. 0 plus 0 is 0, and 0 written as a 3-bit number is this. Down here is 0001, right? So don't think about this as 2 numbers. Think about this as a circuit with 4 inputs. And so first we're just enumerating all of the ways we can write those 4 inputs. The order I happen to do it in is this that you see, and you know, this would continue with 1001, 1010, and so on. Well, I mean, we can put these in. That's not giving away any secrets. How's that? Fewer typos. All right, that should make more sense. So there's all the different input combinations, and so yes. So thank you. Yeah, those should have been swapped. So here B is a 1, A is a 0. Here B would be a 1, A would be a 1, and so on. Is a normal 4 inputs. The first row has 8 zeros, and the second row has 4 zeros. Okay, good. So, say again? Okay, cool. Got it. Thank you. All right, other questions on this truth table? All right, so this is all related to experiment 2. So design a 2-bit binary adder with carry. It's got a carry because this 3rd bit we can view as an overflow of some sort. All right, so 2 bits plus 2 bits gives us 2 bits plus a carry. So technically it's a 3-bit adder in some sense, but 2-bit adder with carry just means take in 2 2-bit numbers, produce a 3-bit sum. Okay, so clearly identified independent variables and dependent variables, inputs and outputs for the 2-bit adder. That's your system diagram. And then truth table for the system based on defined input output. That's this truth table. I don't know if that's a new question or an old question, but if that's a new question, maybe open up your microphone and let me know, because how did you get the numbers for the first 2 columns? I'm not sure which columns we're talking about. All right, step 3, write the minimized output functions in either POS or SOP using K-maps. So that's you know, business as usual. So S0 equals, S1 equals, S2 equals. You can pick off the min terms on the zeros. You can pick off the max term on the ones. You can pick off the max terms on the zeros. Your choice. and simplify those equations. And some of them will simplify nicely, some of them will not. They're still going to be pretty complex though. But you got to have those equations in your report. Alright, and then this asks, state the literal count and number of gates to implement each of the minimized output functions. So literal count says something like this. Well, let me use F because these aren't going to be the actual S's you end up with. So if you do F1 equals AB or A bar B or ABC, and F2 equals A bar B bar or AB or C bar. So literal count is the number of inputs or complemented inputs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The number of terms would be 1, 2, 3, 4, 5, 6. And then the literal count with term sharing says, hey, you know, we've got an AB here, we've got an AB here, we don't need to build AB twice, so we don't really need this term. So the new literal count would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if we include term sharing. So when the lab report asks you for the literal count, that's what it's talking about. And then the number of gates to implement each of the minimized output functions. So you don't have to draw a schematic, but think about, you know, for these equations, how many AND gates, how many OR gates, how many XOR gates or whatever would you need, and just put down that number. All right, how did you get the numbers for the first two columns? Means the first two columns after the 4 inputs. These two columns. So this column is whatever the value of this 2-bit number is written in decimal. 0, 0 is a 0. This column is whatever these 2 bits represent written as a decimal. 0, 1 is a 1. 1, 0 is 2. 1, 1 is 3. Down here, these 2 bits, which are the bits of B, 1, 1, well, 1, 1 is the binary representation for the number 3. The A bits, 1, 0, while the 1, 0 is the binary representation for the number 2. So even though we're just viewing this as something that eats 4 bits, the meaning of these 2 bits is they represent a 2-bit number A, and these represent a 2-bit number B. Cool. Alright, so we've done steps 1 through 3. You've made a system diagram, you've made a truth table, you've written equations. And your equations will end up in some form. S0 equals this plus this plus this plus this plus this, and so on and so forth. Chances are the equations you end up with after step 3, not the equations you want to use in Tinkercad. It can be a big circuit if you do that. So now in step 4, we're going to change gears. We're going to do something very different. We're going to find a different way to design an adder by using what we know about adding numbers.
You have the lab page up.
Thanks. All right. So we're going to rethink this problem. And imagine you wanted to know how to add 2-bit numbers in school. So just plain old decimal numbers. You want to add, you know, from 00 up through 99 plus 00 through 99. Well, one option would be to make a table with, you know, 0 through 99 on top and 0 through 99 on the side, and then fill in each of those boxes and memorize them, right? And 100 rows, 100 columns, that would be 10,000 boxes, 10,000 numbers you'd have to memorize. That's a lot of work, right? That's basically what we're doing when we design a circuit from a truth table. We're coding that truth table into a physical memory of all the possible outputs based on the different input values. So our circuit is in some sense a memory of, in this case, 48 bits. And that's a big task. Well, we don't do that as humans. We don't have to do that in our circuits either. So for you and I, if we want to add two 2-bit numbers, we haven't memorized what this is. We have a procedure we do. First, we add these 1-bit numbers. 7 plus 4 is 11. We write down that first digit, we carry the 1, and then we say 1 plus 1 plus 3 is 5. Bingo, there's our answer. And all we had to memorize was how to add 1-bit numbers and this algorithm that we use. And the advantage of that is, you know, we could add 6-bit numbers exactly the same way. We don't have to learn anything more. As long as we can add 2-bit numbers, we can do that, we can do that. There's our 11, there's our 3, there's our 4, there's our 3. Okay, that's the way that we're going to design this 2-bit adder. And it's going to end up being simpler and less circuitry. And it's going to end up being more useful down the road. So step 4 of the lab is something very different. Alright, and the circuit that you build in step 5 and the schematic that you come up with in step 4 is not going to look anything like what you do in steps 1 through 3. So here's the big hint to get a good grade on the lab, right? You're going to need to have a bunch of work for steps 1 through 3, which is, you know, this truth table stuff that we've been doing so far. And then you're going to have a discussion where you talk about a different way to do this using what we're about to describe, which is called a half adder, full adder design. And then you're going to have a bunch of other work using half adder, full adder ideas to come up with a schematic. And then you're going to implement that schematic and test it and show that it adds numbers and so on and so forth. So you're going to have kind of 2 different pieces to this whole lab. Alright, so let's talk about this change of gears. So this has to do with something called a full adder. And a full adder looks like this. Has inputs A and B on the top. It has an input called a carry in. It has an output which I'll call a sum. And another output which is a carry out. And this is a 1-bit adder. So it adds 2 1-bit numbers, but it also optionally adds a 3rd bit, which we call a carry input, an incoming carry. And the idea of this is if you had a pair of bits you wanted to add, what should the sum be? 0 plus 1 is 1. What should the carry be? This is 0. So this is really just a 1-bit adder. But if we take a pair of these adders and put them together side by side, and I put a pair of least significant bits here, and a pair of more significant bits here, and I put a 0 into this first carry, and I take the carry out from this and I feed it to the carry in of this, and I take this sum and I call that S0, and I take this sum and I call that S1, and I take this last carry out and I call that S2. Well, this whole thing Works like a 2-bit adder. It's got 4 bits coming in, it's got 3 some bits going out. But this is doing pencil and paper addition of two 2-bit numbers. So suppose I have numbers like 1, 1, 0, 1, and I want to add those together. Alright, we know the answer should be 4, right? This is 3 plus 1. So let's say that this is the number A, and this is the number B. So A0 is a 1, B0 is a 1, A1 is a 1, and B1 is a 0. So those are the inputs going in. So let's look at a full adder truth table. And this is basically adding 2 bits plus an incoming carry. So it's adding 3 bits together. So if I add 0 and 0 and I have no carry coming in, the sum should be 0, there's no carry generated. What about 0 plus 1? What's the sum that should be generated from that combination of inputs? Yep, sum is 1. And what's the carry coming out? Perfect, no carry. And this is exactly the same. It happens to be 0 plus 1 plus 0. But that's the same as 0 plus 0 plus 1. And here's 1 plus 0 plus 0. That's the same thing. Alright, here's where it gets more interesting. 0 plus 1 plus 1. What should the sum be that's generated from that? Yep, so that's a sum of 0. And what's the carry here? Carry of 1. So if I add 2 1s, I get a carry of 1 and a sum of 0. And then our last one, if you're adding 3 1s together, what's the sum and carry here? Right, so 1 0 1, that's a 1 with a carry of 1. So this is our full adder truth table. But if this is what our full adder does, we can cascade these together and make, in this case, a 2-bit adder. So let's see if it works. We're adding 1 1 and 0 1. So A0, A1 is 1 1. B0, B1 is 0 1. Our original carry in, we always hardwire that to a 0. So 1 1 0. Well, 1 1 0, we know it's going to generate a sum of 0 and a carry of 1. Right? It's 2, right? So our sum out is going to be a 0. Our carry out is going to be a 1. So this adder is going to see a 0 and a 1 and a 1. And 0 1 1 should generate a sum of 0 and a carry out of 1. So this will be a 0, and this carry out will be a 1. And so what's our final sum? 1 0 0, which is 4. Hey, 3 plus 1 equals 4. It looks like it works. So you can try some other numbers with this and kind of scratch your heads over it and convince yourself that this is really just doing this. 1 plus 1 is 0, there's our carry. 1 plus 1 plus 0 is 0, there's our carry, there's the last one. So this is sometimes called a ripple carry adder. because the carry sort of ripples its way down from the right to the left. All right, questions up to here? All right, so if you could design a circuit like this, which you can do because here's a truth table for it, and you can do a sum of products, you can do K-maps, you can come up with what your sum is equal to, you can come up with what your carry out is equal to. This is a much simpler circuit than this. So you come up with a design for a full adder, and then if you took two full adders and put them side by side like this, bingo, you've got a 2-bit adder. And that's going to be the preferred approach. So in here, part 4, it says, you know, using the results from the previous part or your research into possible designs. That's what we just did. We just did some research into possible designs. And so the hint here is use a full adder, half adder design approach to simplify and modularize the design. And so assuming you decide to use that approach instead of just writing, you know, 3 SOP equations for S0, 1, 2, you got to describe this in your report. Because this, the equations for this and the circuit from this have nothing to do with this. So the equations you come up with in step 3 will not get you to the final circuit you're going to build. So you have to talk about that in your lab report and say these equations are very complex, so instead I'm going to use a half adder, full adder design. And then, you know, what is a full adder? Here's the truth table. Here's the SOP equations I wrote. Here's the K-maps I used. Here's how I covered the rectangles. Here's the equations I came up with for the sum and the carry out. Now I took 2 of those full adders and I put them together like this, put in a block diagram, right? And now go ahead and draw your schematic. Okay, that's the set of steps that give you a consistent story in the spirit of you know, following this design path. But there's one more simplification we can make. Because this is still going to be a fair amount of circuitry. This is not a horrifying thing to build a circuit for, especially if you think about XORs. Because if you K-map this sum, it's got that alternating pattern, 0, 1, 1, 0, 1, 0, 0, 1. You're going to checkerboard. So think about XORs for that. But this is still a fair amount of circuitry. So we can simplify this further. Bye, have a great day. All right, see you this afternoon. So we can simplify this further. And we can simplify it by the observation that this first full adder, the carry in, is always a 0. Because, you know, when you add numbers, whether you're doing it, you know, with decimal numbers or you're doing it in binary, the understanding is this first digit that we add together, there's no carry that we have to feed into that, right? We always start off with a carry of 0 when we add our rightmost bits or digits. And then if that's something that overflows bigger than 9 for decimal or bigger than 1 for binary, then we get a carry into this next place and so on. But this very first thing, the carry in, is always a 0. All right, well, if we don't need an incoming carry, guess what? We can get rid of this column, and we can get rid of all the rows where the carry in was equal to a 1. And we call this a half adder. And a half adder has only 2 inputs, A and B, and 2 outputs, and so it only has 4 rows to it. Because really, all that this ever has to do is add 0, 0, 0, 1, 1, 0, or 1, 1. Because there's no carry coming in. So it's a much simpler truth table. Right, 0 plus 1 is the sum of 1, and it does not generate a carry. 0, 0, 0 does not generate a carry. 1, 1, the sum of that is a 0, and it generates an outgoing carry of 1. And this is a super duper easy pair of outputs to write equations for. So your final design for experiment 2 will be to build a pair of circuits. This is going to be a full adder. This is going to be a half adder. Half adder takes in 2 bits, generates a sum and a carry. That feeds the carry of the full adder, which takes in that carry in 2 bits, generates a sum and an outgoing carry.
Question.
Sure.
Could we leave the first one as a full adder, but equate carrying in as always being a 0?
You could. You could take the full circuitry for a full adder and use that right here and just connect that carry into ground. And that'll work great. And if you want to do that, that's totally fine. But it ends up being a lot more circuitry because this full adder has 3 inputs and the half adder has only 2 inputs. And this is really just an AND gate, and this is really just an XOR gate. So you can get a half adder with a pair of gates. And it's like 1/4 of each of those gates. But yeah, if you wanted to, for some reason, actually use a full adder here, just connect that carry into ground, works perfectly well. And you still get full credit for that. And in that spirit, right, if you completely ignored full adder, half adder design and just implemented these 3 equations from this truth table, you would still get full credit for that. But you are responsible for understanding the half adder, full adder design that can pop up on tests and such. So it's worth it in this lab to go through the extra steps of doing this, even if you don't mind, writing really complex equations and implementing those in Tinkercad. It's still good practice to do the full adder, half adder design. And same thing on tests. I might ask you about a half adder. I might ask you to write the truth table for a half adder or sketch a schematic for a half adder and such. So make sure you at least understand how that would be used, even if you don't use it. Alright, I believe that's everything you need for Lab 4. And that's everything you need about full adders and half adders, other than the observation that you can continue this process. Right, so there's a 4-bit adder. And I can start with a half adder and just make these full adders. And take each full adder's carry out, feed it to the next adder's carry in. Take the last carry out, that's our final sum bit. Well, this would take 2 4-bit numbers and add them together. So you'll be using ICs for AND gates, OR gates, NOTs, XORs, NANDs, NORs, those basic logic gates, and you're going to use those to create the half adder, full adder yourself. So don't use an add chip implemented out of those fundamental gates. And it's not a horrifying circuit, but it does take a little bit of planning. So you know, maybe put your chips down on the proto board first. Figure out, you do your schematic first. You get your component ID block. You know how many of each gate you need, which tells you how many of each chip you need. And so first thing I would do is probably, get a big proto board and lay out your chips. They have to go across that middle section, one on, on each side. Lay those out and try to place them, where you think they might be near each other in terms of how you're going to connect them. But you've got wires. But at least kind of decide, do I need one proto board? Do I need two proto boards? Maybe you'll use one proto board for the half adder and one for the full adder, because the connection between these is pretty minimal, right? The least significant bits go here, the most significant bits go here. And we really have one line connecting this carry out to this carry in. So maybe putting each of these on a small proto board would make sense. Or maybe you can fit them all on one big proto board. But, spend a little time thinking about like floor planning, how you're going to put these things onto your proto boards. And then, ideally, if you have a hard copy of your schematic, you can, get a highlighter and go over the lines of the schematic as you put the wires into Tinkercad. And then if something's not working at the end, you can look at your schematic and say, oh, I forgot to put this line in here, right? You can highlight the power connections in your component ID block as you make those. You can use the column that says no connection, and if you see that this chip has 3 pins that aren't connected, well, look at that chip in Tinkercad. If there's 4 pins that aren't connected, you missed a connection somewhere, or made a mistake in the schematic, right? So the schematic really works well for wiring the circuit up in Tinkercad. And so the more methodically you can work on this, the easier time you'll have. Doesn't mean there won't be mistakes, doesn't mean there won't be problems in the end, but it will be easier to find those and correct them if you're working from a good wiring diagram, schematic with pin numbers, part numbers, all of that. And that's another part of what you're trying to get out of this course is being able to make that bridge from a schematic to actually implementing. Now in Engineering 270, our circuits are much simpler usually. Most of our 270 circuits have one chip and then maybe some switches or LEDs, because we're working with a microprocessor there. So this is sort of the most intense circuit-wise that you'll get if you're computer science. If you're electrical engineering, you'll get into a whole bunch of other circuits in the engineering courses. All right, any other questions? All right, let's take a 4 or 5 minute break. We'll come back. We'll start the second half of the course. And this is where things get really exciting and super useful and interesting. So we'll come back in about 4 minutes.
Mom's not coming home yet.
Oh, really?
Yeah, and she's doing worse.
That's too bad.
Yeah.
What's going on with her?
It's just hit it.
Just hit her hard.
Yeah, it took longer to hit her this time, I guess. And yeah, she was feeling so good the first day. She thought she was good. So,
That's too bad.
yeah. I asked Mom how her and Owen were feeling because they were both sick.
Yeah.
She didn't answer, so.
Yeah, I should probably try not to think about that too much.
Probably, yeah.
Sequential logic, gotta have any sense, right?
Absolutely.
All right. So the first half of this course, we've been talking about circuits similar to what you did in engineering CSE 120. Circuits that basically can be described by a truth table. So if you know what the inputs are, you know what the outputs are. And these are called combinational circuits because their behavior is based on the particular combination of input values. And that's exactly what a truth table is. It says, hey, for this combination of inputs, here's the outputs. For this other combination of inputs, here's the outputs. But there's a whole different category of circuits which we call sequential circuits. And sequential circuits depend not only on what the current inputs are, but on the sequence of inputs that have been given to the circuit. And typical example of a sequential system would be, a laptop. What does your laptop do when you press the left mouse button? Well, we cannot describe that with a truth table. We can't say if you press the left mouse button, then open up Word, right? That's only the behavior if before we press the left mouse button, we move the mouse so that the arrow is pointing on the Word icon. But if we're inside a document and we press the left mouse button, it changes the cursor to be at the letter that the arrow is pointing to. And pretty much everything we do on a computer has this sequential behavior. Pressing a key, pressing a mouse button, letting time pass, right? The results of those changes to input depend on what the current state of the system is. And so this is going to lead us into a whole new realm of circuit design and analysis around something called a state machine. And the state machine is like a digital circuit, but it has a memory. It has the ability to remember past inputs that it's seen and to change its behavior based on the past. And the quintessential state machine would be a computer, right? So to talk about sequential behavior and sequential circuits and state machines, I want to begin by looking at timing. And by timing, I mean, what does a gate actually do? So suppose we have an inverter, and the input we call A and the output we call X. And a truth table will tell us, here's the behavior. If the input is 0, the output's 1. If the input is 1, the output is 0. So we can draw what's called a timing diagram. And a timing diagram basically shows T running horizontally. And it lets us show pictures of how the inputs and outputs change over time. So A is an input. I can set it to any value I want. So suppose I set my input to 0, and then at some point I raise it to a 1, and at some point I drop it back to a 0. Well, we know when A is 0, X is equal to 1. And we know when A is 1, X should be equal to 0. So in theory, this would drop down to a 0 right here. But in reality, there is a delay. There's a period of time after we change the input from a 0 to a 1. There's a period of time during which the circuitry inside this gate is responding to that change. And in fact, it's going to be a little bit after that our output drops to a 0. And similarly, when our input drops from a 1 back to a 0, the output does not immediately go from a 0 to a 1. It's going to take a little while to respond. And then it will jump back up. And so we have these delays here. Now, how big is this time? I don't know, maybe 5 nanoseconds? A few nanoseconds. Not a huge amount of time to us, but to a computer, a significant amount of time. And what's going on during this time? A is equal to 1 and X is equal to 1. It's violating the behavior that it's supposed to have. During these 5 nanoseconds, the input to the inverter is 1 and the output is also 1. And during these several nanoseconds, the input is 0 and the output is also 0. It's violating the behavior of an inverter. And this, you know, is a minor inconvenience to us. We flip the switch and we want the LED to go off. It doesn't go off immediately. It takes 5 billionths of a second to turn off. Well, we don't care about that, right? That's not going to be significant to us. But let me show you a different circuit. So here's a funny circuit. A is feeding into an AND gate, and it's also being inverted and feeding into an AND gate. And we can find a truth table for this. Well, I'm going to put a little label on this part of my circuit. I'm going to call this A1. And if A is a 0, A1 is a 1. And if A is a 1, A1 is a 0. And X is the AND of A and A1. Well, 0 ANDed with 1 is 0, 1 ANDed with 0 is 0. We would expect this circuit, the output is always low. But if we draw a timing diagram, so here's time running horizontally. And let's take our input A, and let's start off low and then go high and then go low. So what does A1 look like? It looks like the opposite of this, but there's a delay. And so X should be the AND of A and A1. Well, 0 ANDed with 1, that's just a 0, so that's going to be 0, 0, 0. At this point, A is a 1, A1 is a 1. We have two 1s going into an AND gate. 1 ANDed with 1 is 1. So the output of our AND gate is going to go high shortly after this, so maybe somewhere around here. The AND gate will go high. And then over here, A1 drops to 0, and so we have a 0 ANDed with 1, so this will go low. And here we've got a 1, 0, the AND is 0. Here we've got a 0, 0, the AND is 0. Here we've got a 0, 1, the AND is still 0. But think about this. Here's our circuit. Our truth table says, hey, the output's always going to be 0. Our timing diagram tells us, hey, when the input changes from low to high, we get this little spike in the output. It's short. It's a few nanoseconds. But there's a brief moment in time when the output is not 0, the output is 1. So that's called a glitch. And a glitch is an unintended change in the output of a circuit. To us, you know, if we put an LED on here, we're not going to see the LED blink on because 5 nanoseconds is too small. But to a 3 gigahertz CPU, which is doing 3 billion things a second, if this is 5 nanoseconds, it's had time to do 15 things, including notice that the output of X is a 1 and respond to that, perhaps by, you know, sounding an alarm, locking the doors of the building, and shutting the CPU down. So as we start to develop sequential circuits that have a memory, we'll start to worry about glitches. And the fact that these little timing anomalies can have lasting effects. If we have a circuit that remembers and changes its behavior if X is equal to 1, right, this circuit would cause some unexpected result. So this is all a consequence of the fact that these gates take a certain amount of time to react. And we've looked at the data sheet before, and we saw these things like propagation delay from low to high. Well, that's how long it takes for the output to change from a 0 to a 1. And they're non-zero because these are physical devices, right? They're not ideal devices. But it turns out we can take advantage of those delays to do some interesting things. So we're going to introduce feedback. So here's an inverter. And suppose I do this. And suppose in this case I deliberately leave the input unconnected to anything. I don't have a switch over here, but I have the output of the inverter feeding back into the input. What do you think the output would look like? And if you don't know, just make a guess. And we'll analyze some possibilities. Good guess, 0. And it could be a 0. Right? If I don't feed something into the input, I've got an inverter, it's powered, it's got pins 7 and 14, the output might well be 0 volts. But here's what happens. If I have 0 volts coming out of here, that comes down this wire and it goes into the input of the inverter, And I know if I have an inverter and the input is 0, the output will become 1. So the output, which was 0 volts, will suddenly change to 1 volt, to 5 volts, logic 1. And if I have a 1 coming along this wire and that feeds the input of the inverter, well, the inverter takes a 1 input, generates a 0 out, the output's going to go down to 0 volts. And we're back where we started. I have 0 volts coming out here, that's 0 volts going into the inverter, which means the output will be logic 1, which is 5 volts, and the output will go high. So this will oscillate. And it's oscillating in some sense because it takes time for this 0 over here to change into a 1. And if you actually physically build this with an inverter, you take the output and connect it to the input, you don't get this oscillation. You get something, you know, wiggling around 2.5 volts or something. But if I string 3 of these together, I'll actually be able to see this oscillation on an oscilloscope. And it'll be a few nanoseconds from high to low. So we've got feedback in here. This is our first circuit where we have the output of a gate feeding its own input. And so this is kind of a quirky little circuit. Let me show you a different version of this. So what could we guess the output of this circuit might be? Same as the input, right? Well, the input is coming from the output. So if we don't know what the output is, we don't know what the input is. We don't know what the output is. But suppose, just for the sake of argument, that this output was 0 volts. Well, that 0 will feed this inverter, which means this will be a logic 1. And this inverter, seeing a logic 1 in its input, generates a logic 0 at its output. If this output happens to be 0 right now, it will be 0 forever after. But here's a different possibility. Suppose, for whatever reason, this output happens to be a logic 1. Where we're going to have a logic 1 feeding the input of this inverter, so its output will be 0. And the second inverter, seeing a 0 at its input, generates a 1 at its output. So if this output happens to be logic 1, it will stay logic 1 forever. And so we've got the beginning of something that can act like a 1-bit memory. And we know that, you know, if this inverter is trying to generate a 0 and I connect this output to 5 volts, I'm doing something wrong, right? This circuitry is trying to connect this to ground, and if I connect that to 5 volts, I'll draw a lot of current, I could burn out my chip, and so on and so forth. But if I do it really, really briefly, if I actually take 2 inverters and hook them up like this on a proto board, and I just take a wire connected to 5 volts, and I just momentarily tap it right here, my circuit will change to this. That 1 will feed this inverter, which will become a 0. This will output a 1. And when I take that wire away, this output will be a 1. And if I have an LED over here, the LED will be on. And now if I take a wire, I connect it to ground, and I touch the other end of it here just for a moment, that pulls this output low. There's a 0, that gets inverted to a 1, that gets inverted to a 0. My LED will turn off. And so I could build a really kind of poorly behaved 1-bit memory just with these 2 inverters. And to store 1, all I've got to do is momentarily pull this point to 5 volts. And then when I take away that stimulus, it'll still be at 5 volts. And to store a 0, I can just touch this output to ground, and when I take away that wire, this will still be at ground. So this is the building block for all the memories we're going to use in this course. And it's a building block for the state machines we're going to build, This is the kind of circuitry that you find inside cache memory. When you have a CPU and it's got a certain amount of on-chip cache, it's usually built with the circuits that we're going to develop right now, which will be things called flip-flops. But the main memory of your computer does not use this. It uses something that's slower but cheaper, which is a bank of what are called capacitors. So that's dynamic memory, but this is a different kind of memory. All right. Well, having to take a wire and temporarily touch it to the output and hope that your instructor didn't see it, right, is not a great way to use a memory system. So we're going to modify this design just a little bit. Remember, NAND gates and NOR gates can sometimes act like inverters. So let's build this same kind of circuit, but let's use NAND gates. And so here's going to be our output X. And there's a NAND gate, and there's a NAND gate. And I'm going to call this input S, and I'm going to call this input R. And let's look at what this circuit does. So suppose I set S equal to 1. Suppose I put a 1 right here in this well, let's do this. Suppose I set S equal to 0. Alright, so I've got a 0 going into this input of my AND gate. Can I say what the output of this NAND is? S is a 0. We don't know what this input is. Do we know what X is? Almost. So an AND, since we have a 0 going in here, the output of the AND would be 0. The output of the NAND would be a 1, because it's the opposite of an AND. So X will be a 1. And it doesn't really matter what the R input is. Right? Just by knowing that the S input is a 0, I know that my output's going to be a 1. So 0, 0 will give me a 1, 0, 1 will give me a 1. Alright, suppose my input is a 1 and a 0. So S is a 1 and R is a 0. That's going to be a 0. Why? Because a 0 ANDed with anything is going to be a 0, so the output of my NAND will be a 1. So this NAND will have a pair of 1s. The AND is a 1, the NAND is a 0, so that's going to make the output a 0. Alright, so those are fairly easy to convince ourselves. Here's the real weird one. Suppose S and R are both 1. So here's a 1, here's a 1, and we don't happen to know what X is. What is this circuit going to do? This is tricky. Possibly. But there's another possibility too. Could fluctuate. Actually, it won't fluctuate. So here's how we can think about this. If we have a NAND gate with a 1 coming into one input, this looks like an inverter. If this lower input is a 1, 1 and 1 is 1, the NAND's going to be a 0. If this lower input is a 0, 1 and 0 is 0, the NAND's going to be a 1. So with both of these inputs set to 1, this is what the circuit's acting like. we're back to our pair of inverters. And whatever the current value of X is, that's the value that will be in X forever. So by putting both of these inputs to 1, we can make this thing look like a pair of inverters, but we have the ability to temporarily force the output either high or low. If I drive this input to a 0, my output will go low. If I drive this input to a 0, the output will go high. And if I leave both of these inputs at 1, the output will stay wherever it was. So this will be, you know, whatever X already is. So this is something called a gate. And in particular, this type of gate is called an SR gate. And when we draw these, we typically draw this with bars over the S, and there's not really an inverter going on. This is just a different symbol. But we put the bar over it to say, hey, this thing is active low. In other words, when S goes low, that's when the output gets set. And when R goes low, that's when the output gets reset. And so we can draw a block diagram of this if we forget about what's going on inside, and we can draw this SR gate. Like this. And the idea is, if you want to set the output to a 1, pull this low. If you want to set the output to a 0, pull this low. And if both of these are high, the output is just stable. It's whatever it was the last time that you either set it or reset it. So it's a 1-bit memory. And we typically draw these pictures a little differently. Instead of drawing them in this linear fashion, you'll see these drawn like this. And so here would be our output X. This would be the set bar input. This would be the reset bar input. It's exactly the same circuit as that. I've just taken this and moved it down underneath. But you'll see these sort of cross-coupled inverting gates. And so this is one way to build a memory. We can also use NOR gates. And the logic changes. We'll end up with, if we set this to a 1, the output will get set. If we set that to a 1, the output will get reset. So that's a gate, or sometimes it's called a latch. And so we have different kinds of gates or latches that we can build. So this one, we have a pair of inputs, and if we want the output to be 1, we pull this low. If we want it to be 0, we pull this low. And that's not bad. That works for a memory. But more often, what we have is a system where we want to say, hey, here's a bit, remember it for me. Well, here's a circuit that says, if I pull this low, I'll remember a 1. If I pull this low, I'll remember a 0. But we could use this to make this thing that says, hey, here's a bit, remember it for me. And so we can make something called a D latch. And this is going to look something like this. We'll have some input D. And we'll have an input called load, and we'll have an output X. And the idea here might be, when this load line goes high, I want you to remember the value of D. If load is low, just remember whatever value you remembered before. But when the load line goes high, it's like opening up a gate, right? So you've got a field and you've got cows outside. You open up the gate, the cows can come into this fenced-in area. And then when the gate closes, whatever's in that fenced-in area is in there, right? I'm thinking Minecraft right now. So this is basically, when you set this to a 1, the D value comes in here and becomes the value that's stored inside this box. When the load line drops to a 0, whatever the value of D was that last came in, that's the value that's stored inside. And we can build this out of an SR latch by doing something like the following. So let's take D and load. And so if load is high and D is high, the output of this NAND gate will be a 0, and we'll connect that to this set input on our SR latch, and that will set the latch. And if the load line is high and our D input is 0, meaning that the inverted input will be 1, then the NAND will output a 0, and we'll feed this to our reset input. And so we can build our SR circuit, using this kind of design. And if we take our D and load inputs here and feed those into the S and R inputs of a latch, and then generate the output here, now we've got this D latch. And a timing diagram might look like this. So let's suppose that our output just happens to be low to begin with. And our D input, could go high, could go low, could be doing any number of things, has no effect on the output. Right? If the load line is low, the output is just whatever it was before. But once the load line goes high, the X output matches the D input. Right? Any cows that wander into the field end up in the field. And then when the load line drops, whatever the current value of the output is, that's the value that's stored, and the D input is ignored again. And then when the load line goes high, whatever the D input is, that's what the output becomes. And it will match. And then when the load line goes low, the D inputs are ignored again. And yeah, there's definitely still a delay here. So the behavior here is when the load line is high, right, the output matches the input. When the load line is high, the output matches the input, with a little bit of delay. When the load line is low, the output is latched. In this case, the last value for the output was high when the load line dropped, and so the output stays high, regardless of the D input. So we've got a memory now. All right, other questions on what we've done so far? This is just going to be a big process of building up on top of these ideas to new ideas. So this gives us a way to store information, right? If I have a data value that I want to remember, All I have to do is bring the load line high and then drop it, and that current value of D will be stored inside this circuit. And you know, if D is a 1 right here, when I drop the load line, that 1 is latched inside this device. But the timing on this can be tricky, especially when we try to build a computer with this. So think about, you know, your favorite programming language, and you say something like x equals x plus 1. X is like an integer or something. And our intent here is take the current value of x, add 1, store it back in x. Right? Mathematically, this is gibberish. If you were in an algebra class and you wrote x equals x plus 1, you got a red x on it, right? Because x can never be equal to x plus 1. But this is really an operation. It's saying take x, add 1, store that into x. What would that look like inside a computer? Well, we might have some memory that we think of as x, so maybe a collection of these D latches. And we have the output, and we have an adder, like our Lab 4 adder, right? But a 32-bit adder. And so we have, you know, one number coming from this memory X, and we have another number B, and maybe we just feed a 1 into that. And here's our sum, and we feed that back into X. And over here is our load line. All right, well, what's going to happen? X has some value inside. Say it's equal to 7. 7 is coming into this input of the adder. 1 is coming into this other input of the adder. 7 plus 1 is 8. 8 is going to the input of this D latch. The load line is low, so this latch is still stored at 7. But now if we raise this load line high, that 8 comes in and gets stored in here. And we drop the load line, and now we have an 8 plus 1. This will generate a 9. And we have a 9 sitting here. And the next time that we raise the load line, that 9 gets loaded into our latch. And 9 plus 1 is 10. And we have a 10 sitting up here. And so if we were trying to build a computer that could perform this one-line program, x equals x plus 1, right, in some kind of loop, all we have to do is each time we raise the load line, right, we know that the current value of x will get incremented. But there's a problem here. The problem is, as long as the load line is high, the output follows the input. If this load line is at a logic 1, whatever the input D is doing, that's what our output is doing. So here's what actually happens. Let's go back to where x was equal to 7. And 7 plus 1 is 8, and so we have an 8 feeding the D inputs of this latch, and our load line is low. Okay, we want to execute this instruction, so our load line goes high. Well, what happens? The 8 gets loaded into our latch. 8 plus 1 is 9. 9 comes around to the input. Our load line is high, so 9 gets loaded into our latch, so here's a 9. 9 plus 1 is 10. 10 comes around and feeds the D inputs. Our load line is still high, so 10 gets loaded in here. 10 plus 1 is 11. 11 comes around and feeds the D inputs. Our load line is still high. 11 gets loaded into here. And maybe at this point, our load line drops to low. So 11 plus 1 is 12. We have a 12 feeding the D inputs. But since the load line is low, that 11 is latched in there. Well, what just happened? X was equal to 7, we said x equal x plus 1, and now x is 11. It didn't add 1, it added 4. Why? Because our load line was high for too long. It was high for so long that the value coming out of here went around 4 times. So how long should we keep the load line high? Well, long enough for this new value to get loaded in, but not so long that that new value comes through the adder, goes around this big long wire, comes back to the inputs, and gets loaded in again. So if we wanted to build a circuit with this, right, we would need to very carefully control how long we turn this load line high. And that's not easy to do. So that takes us into a whole branch of computer science and digital design called asynchronous logic. And it's a very cool branch, but it's very difficult to work in, and it's not something we want to do at this level. So the problem here is that these latches are what we call level triggered. The behavior of this latch, the way the output changes, is based on whether the load line is low or high, the level, the logic level of this load line. What we'd really like to do, this business of taking this current value, adding 1, feeding that to the inputs, and then loading this in, instead of having that happen as long as this load line is high, we'd like to do it at an instant in time. So we'd like to use a type of logic called edge triggered. And our goal would be at this point right here, when the load line changes from 0 to 1, that's when we take the input and we load it into the output. And after that, if the load line stays high, no effect. So for these gates to be usable, these memory devices to be usable for building sequential circuits, we need to move from this level triggered to this edge triggered behavior. And here's what we would like. So here's the D input, here's our load line. And here's our output X. Let's suppose X begins low. At the point where the load line changes from 0 to 1, that's the instant where we want our circuit to look at the D input and say, oh, at this moment D is a 1, alright, D is a 1. And it's just going to stay a 1. And it's going to continue to ignore all those changes in the D input until the next moment where D changes from a 0 to a 1. And at that moment it's going to look and say, oh, D is low, okay, I'm going to go low. So this is edge triggered. All right, fundamentally different behavior. So this is level triggered. And terminology might be our latch is open, or our gate is open as long as this is high. And while it's open, the output just matches the input. With an edge triggered, our gate opens for a really tiny amount of time, right? And during this brief moment where our edges are changed from 0 to 1, we look at the D input, and that's the value we store in this memory. And that's it. That's the value in the memory forevermore until this load line changes again from 0 to 1. And at that instant in time, we look at the D input, it's a 0, okay, we'll remember a 0. All right, that's the basic setup of an edge triggered device. And so these edge triggered devices are called flip-flops. All right. So how do we analyze these? We'll look next time at how we can build a flip-flop using using these level triggered devices. But let's look at particular types of flip-flops, and these are the ones that you'll encounter in your homework. So the first type is a D flip-flop. And that's this behavior that we've just described. And with flip-flops, the load line is usually called a clock. And the output is usually called Q. It's convention. And so here's a typical picture of a D flip-flop. We have a D input, and we have a clock, and the clock is drawn with this little triangle here. The triangle tells you it's edge triggered. It means things are going to happen when this clock changes from 0 to 1. And then we have an output Q. And rather than draw timing diagrams for these, we make a modification to our truth table. And so a truth table for a D flip-flop might be something like this. So if the clock is 0, it does not matter what the D input is. And so we usually do something like this. So Q plus means the new value of Q after something occurs. And this is saying, hey, if the clock input is a 0, does not matter what the D input is, right? The new value of Q is going to be the same as the previous value of Q. So this is like new Q equals previous Q. If the clock is a 1, the D input doesn't matter. The new value of Q is still the same as the previous value of Q. But when the clock changes from a 0 to a 1, right? So this is saying clock changes from 0 to 1. So this is that positive edge in the clock. If D is a 0, Q becomes a 0. And when the clock changes, if D is a 1, Q is a 1. And usually it's understood that if the clock is not changing, Q is not changing. So these first two rows, we wouldn't even list. And so here's a more typical truth table for a D flip-flop. So here's our clock input, here's our D input, here's the new value of Q. And there you go. When the clock changes from 0 to 1, if D is a 0, Q becomes 0. If D is a 1, Q becomes 1. So that's a D flip-flop. All right, and there's a few different kinds of flip-flops. There's also something called a T flip-flop. And a T flip-flop has a clock input, and it has a T input. And if T is 0, when the clock ticks, nothing changes. The new value of Q is whatever the old value was. But if T is 1 and the clock ticks, the Q value changes. it toggles, or flips between 0 and 1, 1 and 0. So in this case, if we drew a timing diagram, and usually our clocks are repeating like this, and here's our output. Let's suppose our output happens to start low. If t is low, the output doesn't change. If t is high, each time the clock changes from 0 to 1, the output changes from its current value to the opposite value. Here's another event where the clock changes from 0 to 1. T is high, the output toggles. Right? Clock changes from 0 to 1. If t is 1, the output becomes the complement of its current value. Here's another point where the clock changes from 0 to 1. T is high, the output will change to its opposite value. Here's another point where the clock changes from 0 to 1. T is low, the output just remains whatever it was. So there's what a typical timing diagram might look like for a T flip-flop. Alright, so there's two other kinds of flip-flops that we'll talk about sometimes. There's an SR. And a lot of times we don't even include the clock column, because generally things only happen when the clock changes from 0 to 1. And so with an SR, if both inputs are 0, the output is unchanged. If R is 1, the output is reset. If S is 1, the output is set. And if both inputs are 1, it depends. Sometimes this is simply called a forbidden state. Sometimes your truth table may say, in this case, the output will become a 0. And we'd call that a reset dominant circuit. Sometimes it might say, hey, if both of these are 1, then the output will become a 1. The set takes precedence over the reset. But rather than deal with this ambiguity, sometimes we use sort of the greatest of all flip-flops, which is a JK flip-flop. And a JK flip-flop, if both inputs are 0, nothing changes. K is like a reset, forces the output to 0. J is like a set, forces the output to a 1. But if both inputs are 1, this acts like a T or toggle flip-flop, and the output will toggle. And this is the most useful of all our flip-flops, because it gets you the behavior of a SR and a T, and in some sense a D also. Alright, one more piece of information you'll need for some of the homework, and this should give you enough to at least get started on the homework. There's 4 questions for homework 4 assigned for this week, 1, 3, 4, 5. But one extra detail. The behavior of the circuit is based on what happens when the clock changes from 0 to 1. Right, for all of these devices. For a T, when the clock changes from 0 to 1. If T is 0, the output's stable. If T is 1, the output flips. But for a circuit to work correctly, you're not allowed to change T at the same time that you change the clock. And in fact, T has to be stable for some period of time before the clock tick. Right, so you're talking to a friend, you're playing a weird game where you say, okay, I'm going to tell you a number, I want you to remember it when the clock chimes. Right? So I'm just going to keep saying numbers, and like as soon as the clock chimes, whatever number I'm saying, that's the one I want you to remember. So you say 42, 17, 5, 11, 13, chime. your friend remembers 13. All right? But what happens if just as the clock is chiming, you change from 13 to 95? Which number would they remember, right? So there has to be some period of time before the clock ticks during which our input's not allowed to change. And this is called the setup time. And similarly, after the clock ticks, there has to be some period of time during which your output does not change. And that's called the hold time. And these are the main timing constraints with flip-flops. So in theory, right, at the exact instance where the clock changes, that's the only time the value of t matters. But because these are physical devices and things take time to process, our input needs to be stable a little bit before and a little bit after the clock tick. Okay, the amount of time it has to be stable before, I don't know, 5 or 10 nanoseconds, that's called the setup time. And how long you have to hold that input at its value after the clock tick, that's the hold time. It's also a few nanoseconds. But these will end up being critical times because these will affect how quickly we can run a computer. The clock speed of a computer is really a function of the setup and hold times and the propagation delays from inputs to outputs in the logic gates. And we'll take that apart in a lot of detail on Wednesday and see specific examples. All right, so this was a first pass through the building blocks of sequential logic. This should let you at least take a look at questions 1, 3, 4, and 5 from homework 4. Bring some questions to office hours tomorrow if you like. We'll dig into this more on Wednesday, and then we'll start using these to build these sequential circuits that we call state machines. So, all right, cool. That's all we got time for today. Hope everyone has a great afternoon, and I will see you next time.